Section 2.5 is we're going to continue doing the proof, and notice it's talking about proving statements about segments, which if you think about it, we've already done some proofs with segments. We're just going to kind of throw in some little bit different ideas. A lot of what we're doing today is just kind of more examples of what we've been doing the last couple days.
Okay.
So again, not really throwing any new information at you, just trying to get you more and more comfortable with this idea of a geometric proof. Okay. Now, this first slide, you'll notice there is a new vocabulary term. We haven't had a vocab term in a while. But the cool thing about this vocabulary term is that it's actually a vocab term that you guys have seen before, theorem. Can you think of a theorem that you already know of, Mrs. Hochgravy, out there?
Well, I'm trying to think.
There's a pretty popular one that you've already learned in algebra.
There is, huh? Oh, like maybe the Pythagorean theorem?
Yeah. Now, that's just one of a lot of theorems that we're going to learn.
Okay.
Right? So what a theorem is, it says it's a true statement. Okay? So it's true. We know it's factual. It's something we can work with. And it comes from a result from another true statement. So a lot of times theorems come from things that you have already seen as happen, and we create a new rule off of it.
Okay.
And they're very useful for proofs. We're going to use theorems a lot in our proofs as we get, especially next section. Not as much today, but in section 2.6, you'll see that. Theorems have to be proven. So one thing that often people get confused about is what's the difference between a postulant and theorem? Because postulates are also true statements. They're rules that we use in math. Theorems are also true statements. They're rules we can use in math. But what's the difference?
Well, we said the postulates were like the no-brainers and they didn't have to be proven.
Exactly.
Where these sounds like these have to be proven.
So, and some theorems are pretty easy to make sense of. They're logical. Some are a little bit tricky to kind of see where it came from. So we'll often prove some theorems throughout this year. Not every theorem will we prove as a class just because we don't have the time for it. Again, they can be used as reasons in our proofs. So far we've used what kind of reasons in our proofs?
So far we've used definitions, we've used postulates, and we've used some different properties like symmetric or transitive or
apo,
espo,
more the algebraic. So because we're going away from algebraic proofs, we're not always going to use properties of quality. So that's why theorems are going to be handy for us.
Okay.
So just to give you a kind of a brief overview of that.
So if a theorem is really just like showing a logical or taking out the steps of a logical argument that we would have, it's really just making a shortcut almost, right?
It is. And you'll see that once we actually start using theorems, it will allow us to do that shortcut.
I like it.
And
okay.
Right now you're kind of like, well, what does that mean? When we actually put one to use, you're gonna really like theorems.
Okay.
When we learn several a day sometimes.
All right. The first theorem that we're going to be talking about is talking about properties of segment congruence. Today we're going to focus on proving segments to be congruent a lot. And we've talked about a lot with segment equality. We've used this word congruence before. We know that if measures are equal, then their segments are congruent. But these are properties, reflexive, symmetric, and transitive, that we've looked at with equality, but these are also properties of congruence. So segment congruence is reflexive, it's symmetric, it's transitive. And I have some examples just to show that. For any segment AB. Oh, I guess I used the word segment AB. That's why I didn't have it there. For any segment AB, we know that it's congruent to itself.
Now we've seen reflexive property before.
We have.
And we used it, like you said, with equality. So it's just now you're saying that this works for congruent statements as well?
This works for congruent statements as well. Now, what we need to be careful with is if you have one statement that's congruence and one statement that's equality, we can't put them together yet. Okay. But they can be in either equality or incongruence form.
Okay.
And you can use these properties.
Awesome.
Okay. Now, the symmetric property is the one that says that if I have two segments that are congruent, I know that I could reverse them. And that's just like what we looked at with equality as well. So the order of those two segments won't matter. The transitive property is also a property of congruence, where I can say that if I know two segments are congruent and one of those segments is congruent to something else, well, I know that if two segments are congruent to the exact same thing, then they're going to be congruent to each other, just like we talked about with equality. One thing I want to point out, notice that the word substitution is not up here.
Yeah.
Substitution is not a property of congruence. It is only a property of equality.
And when we're adding to both sides, that only works for equality as well. Like
yeah,
the
it
APO
does,
and
because
stuff.
if you think about it, you can't add segments, you add their measures. So measures, when we're talking about the segments measures, that's when we talked about equality. So we can add things when they're in that equality state, but not in congruence.
Okay, so these are the only ones that all the properties of equality that we learned the other day, these are the only ones that work for both.
Right.
Okay.
That's absolutely correct.
That's good to know.